Well, hello. Welcome to Exida's webinar. We have about 1 more minute to go by my clock. I'm going to wait until it flips over to 10. My name's Bill Goebel. I'll tell you a little bit about Exida, and then we'll talk a lot about SIF design verification. I'm glad you're here. Thanks very much. Just checking on my status screen. Everything looks green to me. This is good. All right, let's go ahead and get started. I feel like saying, for those who just joined us, I feel like saying, hello, my name's Bill Goebel. Today, we're going to talk about safety instrumented function verification. We're going to talk about the essential engineering duties. I mean, this task is important, and I'll explain why. And then I'll talk about the kind of things that I do, and that it's essential that everyone who does SIF verification perform these tasks. Well, as one of the co-founders, I'm proud to say that over the last 21 years, Exida has grown to become a global solution provider. We're very pleased with the way things have gone. We have an engineering tools group that creates tools for systems level functional safety tasks, Excellentia, and SILSTAT to collect field failure data. The engineering tools group also has a set of tools for product developers, those who create new devices for functional safety and cybersecurity. We were quite pleased that in 2015, the ARC research group did a study on safety device certifications, and they discovered that Exida was the global leader, in spite of what most people thought back then. Even in the logic solver category, we were just ahead of our nearest competitor. Most of you know that we call ourselves a knowledge company. We study a lot of incident reports. We study a lot of field failure data. We take that data, turn it into information, and then we publish it in our books and our white papers and our training courses. Well, we all have to work to make the world a safer place. One of the things that has become very clear to me, is that the functional safety standards we have implemented today actually have a very ingenious method for managing risk. When I compare it to the way things used to be, it's so superior. And it all started in ISA's S8401 standard, published in 1996. And as you'll see, it's a three-step process. The owner operator analyzes the risk of the unmitigated system, and if that risk is above tolerable risk, a risk reduction need is determined for a particular application. And then that risk reduction is converted into a safety integrity level. The beauty of that is that companies don't have to publish, or they don't have to publish their inherent risk or even their tolerable risk, only the risk reduction. To me, that was a huge breakthrough, because I remember all the fighting about that issue. IEC 61511 then follows through with an engineering process with rigor according to the SIL level. The probability of failure requirements vary with SIL level, and operation and maintenance requirements vary with SIL level. This approach is called performance-based. Performance-based. You know, there are no predefined designs. There are no predefined architectures. The favorite design of a committee member is not in there. You are free to implement what you believe is best, but as we will quickly learn, you have to demonstrate via the performance metrics that your design meets the safety integrity level. There are three essential engineering verification duties. Given a safety function design, we want to check the systematic capability, item number 1. Item number 2, we want to calculate probability of failing dangerously. And number 3, we want to check the architecture constraints tables. And we're going to focus today on item number 2, the PFH, because that's kind of the hard one. The other 2 are relatively straightforward. Do you see what this performance-based standard really gives us? It allows us to optimize our designs. Designers, owner-operators can make trade-offs between operating expense and capital expense, and you can optimize the design. You can have more proof tests and spend less money on equipment, and there are all kinds of options. Now, all you have to do is show that you meet the performance criteria, and it's really great. And it allows innovation, it allows new things, and quite frankly, the innovation in the automobile industry is going to help all of us. However, it doesn't help anyone if you don't do a good job of verifying that your design meets the safety integrity level. You must check if failure data you are given is intended for the application. I wouldn't use failure data for clean service water on the wellhead of an offshore platform. That makes no sense. The failure rates are going to be very, very different. You need to make sure your failure data includes all the real failures. I mean, think about it for a minute. What are we trying to calculate? A probability that we have a failure on demand because a manufacturer made a mistake? Or are we calculating probability that we'll have a failure because of any source and cause? The latter is obviously what I think was clearly intended by the standards. I mean, you don't get risk reduction if you only calculate probability of failure based on manufacturing defects. There is a group of people who feels that way in the world, but I'm not one of them. And you got to make sure, if you possibly can, to match site operation and maintenance capability. Now, that might be new to you, and if you want to learn more about it, exida has 2 white papers and several webinars on our site. The bottom line is exida's looked at thousands of field failure reports, and we've clearly discovered that the exact same manufacturer model number may very well have different failure rates at different sites. And it depends very much on a variable we call operation and maintenance capability. So we call it the site safety index. You can read all about it. Now, the optimization granted by our performance-based standard does depend on realistic failure data. A realistic prediction requires that we use realistic data that includes all failures, matches the application, and considers the site maintenance capability. So the big question is, where do we get that data? Well, those of you who have watched some of our webinars before know that there are 2 fundamentally different techniques, estimation and prediction. Let's talk about estimation first. Estimation is the statistical analysis of field failure data, and obviously it can be used to generate good quality data. However, I was once told by an OEM engineering manager that I can hire a statistician to give me any answer I want. Doesn't sound good for statistics, and I thought to myself, what is he talking about? And I realized it all depends on the statistics are just fine, the methods are good, but it all depends on the assumptions the guy makes or the person makes. Good failure rates can be estimated if the analyst knows how the equipment operates, knows the key environmental variables, and knows how the equipment is used and how the data will be used by designers. This reminds me, I once heard a quotation attributed to Mark Twain, but actually I think it was someone much earlier. There are lies damn lies, and statistics. I know I first heard it from Paul Gruen in an ISA course. And that doesn't say much about statistics either. Maybe we ought to change it till there are lies, damn lies, and assumptions. I say math is not enough. Always check the assumptions. Manufacturer field failure return studies are the most common type of estimation because manufacturers collect field return information, and that is a valuable source of data. However, there are very strong limitations because not all failures even returned items, not all returned items are counted because many are marked no problem found. Not all failures are returned to the manufacturer. Maybe that's the biggest variable of all. And the manufacturer really does, in most cases, does not know the actual operating hours. So the only way we can use this data is to make some assumptions. But I have to admit, when I worked for a manufacturer, I was taught to make some quite unrealistic assumptions to make the products look good. So we have to be very, very careful with manufacturer field return data studies. I can show you an example, and I think the key is you'll really see what kind of thing goes on here. This is a set of compiled manufacturers' return data and a set for over a 3-year period and an estimate of the operating hours. Now, we checked their assumptions on operating hours, and they weren't bad. We redid the calculation based on our assumptions. And we do this as part of our FMEDA verification technique. Now, we don't use this to generate our failure rates. I'll tell you more about that in a bit. There's 188 returns, but for 48 of them, no fault found. Okay. Maybe we can exclude those, although I might want to dig into the way they test, but let's assume right now they do a good job testing and somebody returns something that worked perfectly. Fine, we have 140 left. But if you look down through this list, you can see that, whoa, damaged by customer, bent pins, broken fuse, splintered wiring. Okay, look at all this. So what if we only define failure as those failures caused by the manufacturer? How many of these items can we get rid of? Well, let's start crossing out all the ones marked damaged, the ones that seem to be caused by the end user. Damaged by customer, damaged beyond economical repair. Oh my, damaged, broken, out of calibration. At this point, if we throw away all these failures, the failure count drops from 140 to 62. You know what that means? It basically means the calculated failure rate will be less than half of what it realistically is. I mean, if it's out of calibration and the safety function doesn't provide protection, you might have an accident unless there's another layer of protection. So I don't think anybody wanted to calculate the failure rate of a probability of failing dangerously with only failures caused by manufacturers' data. Who would use that technique? Well, there's a lot of people. There are people who do. I was looking at a certificate from a German certification body, and it provides data for 2 types of ball valves, a floating and a trunnion. And it's interesting data, but I look down at the bottom and there's a little statement, and I'm going to blow it up so you can really read it, I hope. It says the stated values are the results of analysis of field failure feedback. Okay, it must be the manufacturer's data. Random and systematic failures, which are the responsibility of the manufacturer, were examined. Uh-oh. This analyst only calculated failures that were the responsibility of the manufacturer. Now, the statistics are technically valid, and the certification body has been quite forthright and honest by telling us what he did. But what does this really mean? It means the failure rate data on this certificate is likely less than half of a realistic number. And you could use this data if you had a site that never made mistakes, that had perfect operations and maintenance capability. That's what exida calls SSI4. I guess many people in the world are convinced SSI4 cannot be achieved. But if you did, and now if some customer came up to me and said, oh, I have SSI4, and it says, you got to send me a letter telling me that you have SSI4 before I'll use it. Because if there's ever an accident, I got to have some evidence that I didn't make this bad choice. All right, that's estimation. A very quick view of estimation. We have other webinars on the subject if you'd like to dig in deeper. Prediction is a better technique in general because by the time you get enough data for estimation, some products are completely obsolete. There are 3 techniques that are being used. 2 of them are common, the B10 data based on cycle testing, but I hope by now you've looked at many of our webinars on cycle testing and you know B10 is only useful for devices with nearly continuous movement because they assume all failures during useful life are due to premature wear out because of a manufacturing defect. Any other failure like corrosion, stiction, binding will negate the assumption and the method, and therefore you cannot be using this kind of data. The FMEDA predictive method is the other very popular method, and it's a technique that combined a number of existing techniques back in the 80s. The component failure modes and failure rates are looked at one at a time, and the impact on the device is determined. When you add that all up, you will have a failure rate for each failure mode, a diagnostic coverage, the useful life, and a proof test coverage of any device. Now, it's a bit tedious. I don't really like doing it myself, but fortunately at exida, we have several people who are really good at it. The component database has to have all the parts you're going to use and so forth in it. And so the bottom line is the component database is a really important part of FMEDA. In fact, maybe the whole foundation of FMEDA. With the wrong component database, data based on consumer applications or military or telecom, the wrong stress factors in an FMEDA will produce poor predictions. So how do we overcome this problem? And of course, we have to meet the 61511 requirements for field failure databases. Bottom line is estimate and prediction can be combined. If both estimation and prediction are good, the results should be equal for a given device at a given set of parameters. If we combine estimation and prediction, the best possible results can be obtained. There is a method that does that, and we call it calibrated FMEDA. It's hard to compare FMEDA results to field failure data, but if you study and put in enough time, it can be done. Remember I said estimation should match FMEDA prediction. But what if it doesn't? Well, you have to launch an investigation. You have to figure out why. Did you interpret the field failure data wrong? Is it a different set of parameters, application or environment? And then, or does your component database need to be updated and changed? And in this closed loop system, which can work very, very well, closed loop, after a period of time, the results get really good. Exida does this. We've done hundreds and hundreds of these comparisons, and we've even published quite a few papers on those if you want to go look at our website again. There are certification bodies, including Exida, that use the calibrated FMEDA method. And it is based on a lot of field failure data. You can see on the right-hand side that this particular certificate is a trunnion-mounted ball valve. We're going to come back to this later. But I do see a lot of different failure rates there. Those are different applications. A full stroke, clean service, or tight shutoff required clean service, or open to trip and clean or severe. This is really great because I can match up the failure rates to the application parameters. Now we take all of these FMEDAs and all of our field failure studies, and we combine them into an analysis technique we call predictive analytics. We do statistical analysis on the FMEDA output and on the comparisons, and we have used this to create an upper bound and a lower bound for any particular device. Now, why did we do this? This data is available free of charge, and we had some customers, some end users, and some engineering companies that were really struggling to verify the quality of their data. And so we created this website to give them a general tool to do that with. For example, for any particular device, you will see a dangerous detected low bound and a dangerous undetected high bound. For a pressure switch, it should be between 50 and 1,000 fits. Okay, for a smart temperature pyrometer, I see 200 to 460. For a safety certified temperature transmitter, I see it should be between 25 and 90. That's based on basically plus or minus 3 sigma of the FMEDA results conditioned on field failure results. Now here's the set we have it for sensors, logic solvers, and final elements. Now here's a set of information for some valves. Anytime you want, you can go online and look at all this information. We keep it up to date. We update 2 or 3 times a year. At any moment in time, it might be a little out of date. I found that, but it's still very, very good. Now, how do you validate the failure data you have? Because it's your job, your responsibility, and your ethical obligation to make certain you are using data that is valid for your situation. Well, we already know that in the process industries, for sure, the B10 cycle the B10 cycle test is not useful at all. And we have to be very, very concerned about manufacturers' warranty data studies. We need a checklist. Are all the real failures counted? Are the operating conditions similar? Are the environmental conditions similar? And is the application similar? And lastly, we need to check the given data against SIL-safe data. And if it meets all of this criteria, it's validated. Let's take a look at some examples that I have received over time. A manufacturer published a independent third-party analysis that shows 17.3 fits as the dangerous failure rate for a pneumatic actuator. In case you couldn't read it, I better blow that up. 17.3 fits. Now, I could not get the assumptions, and I could not get a report that showed us the methodology, but it feels like this estimate is likely to be dangerously low. So let's check it against our criteria. Are all real failures counted? Well, if it's manufacturing data, probably not. Are the operating conditions similar? I can't tell. I don't know what the environmental conditions are, and I don't know if the application is similar. It just wasn't enough information. So we're going to check it against SIL-safe data, and this is a spring return pneumatic Scotch yoke. That number should be at least 400. This is a big problem because if you use this data to do a SIL verification and say you meet SIL 3, your field failure, your field performance won't not be even close. This is not okay. Let's check a certificate. This certificate uses the calibrated FMEDA technique. And I do see that different failure rates are given for different applications, which is good. So let's go through our checklist. All real failures are counted, yes, because they are in the calibrated FMEDA technique, because the comparisons are based on real field failure data. And that data is always end user induced and manufacturing defect are always included. Are the operating conditions similar? Operating conditions are given in the profile of the FMEDA report, so we know what that is. The environmental conditions are specified in the FMEDA report, and the applications are given. And what I'm talking about is spring return or double acting, single piston, double acting, double piston, and an adder if you have a damper. And is it pneumatic or hydraulic? So we have different failure rates for all those situations. And let's go to the top line, spring return, pneumatic, go all the way to the right, 427 fits. 427, it's above 400, yay! It's very likely to be valid. We're going to accept this data. Example number 2, a certification body report, an accredited certification body. Now, we get the report, we look through it, it's floating ball valves and trunnion ball valves. It says all the calculations have been done with field experience and the reliability data given in reference 11. And I looked that up, and that's a report that the manufacturer provided. So in this case, the manufacturer did not even provide the raw data, just a report. So the manufacturer, we'd have no idea if all the real failures were counted or not, but it sure looks like they weren't. We could probably look up the operating conditions and if there are any environmental restrictions, but if I have a tight shutoff application, does this data apply to tight shutoff or just clean service or higher leakage? And we have no idea. But we got to check it against SillSafe data. Now this is a, we have all the data here for trunnion and ball valves. The trunnion ball valve data was given to vary as a function of model number between 95 and 200. And I'm talking about the upper limit based on their 90% confidence factor, not the numbers highlighted in yellow. But SillSafe says 400 to 900. The floating ball valve has upper bound 11.68 to 25.5. This is not good. Oh my. Yeah, I see it there at the top 2 lines. And SillSafe check range is 300 to 900. So obviously this data is not okay. And why? Probably because it's from a manufacturer's return data study and with all the analysis done by the manufacturer, probably the way I was taught when I worked there. I don't know that, I'm just guessing. Here's another certificate. We looked at this briefly. The data was given for 2 types of ball valves, 210 fits for a trunnion and 109 fits for a floating ball valve. We already told you that the method was statistically valid and the analyst was very honest and forthright by telling you that only the manufacturer's failures were examined. This statement means that the failures caused by operation and maintenance were excluded. This data is only valid when the site has perfect operations and maintenance. And we already talked about that. Now, let's go through our checklist. Are all the real failures counted? It says right in there, no, they weren't. We're not sure about the operating and environment because we're not sure about the application because I don't see any numbers for tight shutoff versus normal. I don't see any numbers for clean service versus severe service. Now let's check against SIL-safe data. For the trunnion, the certificate from an accredited certification body is 210, and yet SIL-safe data says 400 to 900. For the floating, it's 109, and it should be 300 to 900. So obviously, this is not okay. Why is this not okay? Because all failures were not counted. Not because the analyst was incompetent. He probably was told by the manufacturer, no, only count our failures. I wouldn't do it even if I was told, but that's what I saw on this certificate. Now let's check a calibrated FMEDA for a trunnion mount ball valve. I see that the result, if you look very closely, there's a lambda D at 505 fits for clean service, and it goes up to 898 fits for severe service. And of course, the numbers go up even higher for tight shutoff, which makes perfect sense. Let's check this and assume we're not using tight shutoff for now. All real failures counted? Yeah. The operating conditions and environmental conditions are stated in the FMEDA report. Are the applications given? Yep. Let's check it against SIL-safe data. For the trunnion ball valve, the certificate says 505 to 898. SIL-safe data is 400 to 900. Yeah, it's all within range. I mean, that 898 is getting up there. How about for the floating ball valve? Check it again. Well, for the floating ball valve, we have a different certificate. It provides 369 to 693 fits. Let's look. Is that 23? Yeah. It checks against SIL-safe data. It's good. Now you might expect that because we used FMEDA results to produce SIL-safe data. FMEDA results reflect the differences in designs and materials and manufacturing. We've done hundreds and hundreds of them, and those differences are reflected in a statistical analysis of FMEDA results. We tempered that and used a given the field failure data is this, what's the probability that the FMEDA data is correct? And at this point, the comparisons are matching up very closely. So we think we have a very nice result. We think it's very realistic and reasonably accurate. So if we look at this data, this 17.3 was by far the most offensive number in the whole chart. The calibrated FMEDA for a similar device is 427. SIL-safe data range excluded the manufacturer's warranty data results. The trunnion ball valve, we had range of numbers between 95 and 210. Calibrated FMEDA was 5 to 900, and it should be 4 to 900. A floating ball valve had an 11.7 to 25. That's not good, but oh yeah, that was based on manufacturer's analysis. They probably didn't count anything. But obviously, even the 109 is roughly less than 1/3 of the calibrated data and almost 1/3 of the lower limit in SIL-safe data. So the bottom line on failure rates are estimation techniques based on manufacturer's return data typically have so many optimistic assumptions that the results are likely to be very inaccurate and potentially dangerously low. Even when the statistical analysis is done by an independent third party or even a certification body. I've heard some people say, hey, I cannot challenge the numbers on a certification body certificate. These people are well known across the world. Yes, they are. And I'm glad they told us what they did, so we know when to use their data and when not to use their data. Some certification body, including exida, is based on field failure rate data predicted by a calibrated FMEDA process. So far, the data will meet all realistic criteria, which means you're really calculating probability of failure on demand for your site. Now, what do you do when all the available data is not realistic? I pick a mid-range SIL-safe data number, or if I believe or a high range SIL-safe data number. In effect, use a high generic number. I know many analysts do that anyway, but if I have good, reliable data, I'm going to use it. So what is an engineer to do? We've got to remember that any engineer performing a SIF verification calculation has the duty and the ethical responsibility to verify given failure data from any source, including exida, any certification body, any independent third-party analyst. Verify the data to make sure it meets your situation. This verification must check applicability of the data. If you have no idea what the site safety index is, use SSI2, which is average. That is the default parameter in Excellentia. Make certain that the function you need in your safety instrumented function matches the data. Is it open to trip, closed to trip, or tight shutoff? Is it severe service or clean service? And the definitions are given. If it seems to me it's right in the middle of clean to severe, you got to pick worst case, severe. Verification must check if the data is realistic. We have provided silsafedata.com for anyone who wants to use it. We believe those numbers give you a very realistic range. Now, I'd like to let anyone know that if they are very interested in learning more about this, exida has a whole series of online self-paced training. This particular subject is covered in FSE 102, and it's also covered in FSE 211. You can sign up for these. You don't have to travel anywhere. You've got 60 days to access and study the information. We also have live courses being delivered online, and we have a full schedule on the exida website. Now, let's just see our time. We have a little bit. I'm going to say thank you for your time. I hope you have found the information valuable. If you have any questions, please, let's go ahead and try to answer them. Options. I have a question button here. Let me hit that. I don't see any questions here yet. But if you have some comments, questions, you might say, hey, what are you talking about? I don't understand. What is this SSI? I can tell you that really the failure rates do change drastically from site to site. PFD for a given safety function changes drastically from site to site. I have so many stories to tell you about and looked at so many field failure reports. It's amazing. If you're looking at this later, and you will get a copy of the slides, and you will be able to access a recording of this seminar so you can go through it again. If you have any questions, please don't hesitate to send us an email about this webinar. You want to challenge something that was said, please send an email, and we will answer your questions asynchronously. All right, I got one here. Just said great web. Oh, thank you. Thank you very much. I appreciate it. We all have to work together to make the world a safer place. Thank you all. I'll wait just one more moment.
Bill, we did have some questions come through.
Okay.
What I can do is I will send you a report of all the questions.
Yeah, sorry. Thank you, Kristen. Kristen is our training coordinator. I don't see them on my screen, but that's all right.
Not a problem. I will forward them over to you, and then we'll get back to you on the answers to those questions.
Yeah, we'll definitely give you written answers to all your questions. And I say thank you very much for all your questions. It'll help us do a better job with all of our webinars and all of our training. Thank you all, and be safe.